from Qualcomm, Germany, which examines the cost of different deployment options for radio access networks. In particular, it contrasts intelligent fixed, decode and forward relay nodes with micro base stations. So, Marc,
Thank you very much. So, welcome everybody. This work has been carried out in the Werner 2 project during the last 2 years, and of course, cooperation with some other colleagues. Two of these from Ericsson have co-authored this paper. So, just a moment. Why are we doing this? So, of course, as the capacity of the networks are constantly increasing and the demand for higher data rates is driving this, the performance versus cost argument, of course, is a crucial design issue for new networks because contrary to earlier times where practically the revenues of the networks also grow with the transfer data rate, in the future it will be the case that the cost per bit will be reduced drastically. So the user is not simply not able or not willing to pay linearly with the increased data rate or with increased data content in the networks of the advanced services. Therefore, the cost issue of new radio access networks is critical, of course, to operators. So in the Werner project, the Werner system is one of these new beyond 3G systems for radio access networks. Of course, for example, like LTE as well. It is a goal to optimize the performance versus cost trade-off. And that can include different types of access points, which can be introduced, and that includes, of course, the normal base station, but also novel types of access nodes like relay nodes. These relay nodes have been also studied in lots of projects, not only in the Werner projects, and lots of talks also at this conference have been dedicated to the relay node technology. So what we will do here is to try to classify cost components that can arise in a radio access network deployment. Then we will show how we can actually model the total deployment cost of the network and also indicate a possibility to optimize the deployment cost of a newly deployed network. We will then show some example cost assessments for different combinations of access point types, so either base stations, relay nodes, micro base stations, etc. There's some previous work on this issue, not very much, but the majority of this work actually indicates that the total cost of a radio access network can be modeled as being linear in the numbers of employed base stations or other access point types, plus a fixed cost term, for example, addressing centralized gateways or nodes such as centralized radio resource management servers, etc. So what do we do to model the total cost now? First of all, we have a certain kind of traffic demand. This traffic demand is derived from a user density and the service partitioning and some other factors that we studied, for example, in the Werner project. So we have some good idea about the future traffic demand produced by the users. Then, of course, we have the radio model, which governs the propagation condition. Depends, of course, on the distance, on the carrier frequency, failing environment, and scenario, etc. That is, of course, also important for the deployment. Then we have a certain deployment strategy. So, for example, it might be a difference if a certain operator has already some 2G or 3 base stations available. He will be very likely to place the beyond 3G base stations at the same place. And that is a totally different constraint compared to a greenfield operator who can basically choose the base station locations from a set of candidate sites, for example. We can then do, if we set all these constraints here, a cost assessment based on the required network elements that are required to cover actually the demand of the traffic. I will show you in this paper how this goes. So first of all, we try to classify possible cost components that can arise in deploying classification can be made according to different classification criteria. You see here at the top of the table, for example, the classes of CAPEX and OPEX cost. That is initial hardware costs, for example, that arise only once, capital expenditures. And then on the other side, you have the operational expenditures, which you have to pay, for example, each year. One example would be the fixed line backhaul connection to each base station, where you have to pay a monthly or yearly rent to the operator of that wireline. So another classification criteria is here listed as the so-called cost group. And here we actually differentiated between the different linearity properties of the costs. So for example, cost group 1 contains cost components that increase linearly in the number of base stations. Cost group 2, costs are proportional to the number of relay nodes, and cost group 3 are the once-only costs that arise only once per network. We also have some system-specific costs and proportional to number of subscribers, but for our study within the Werner project, we only addressed here these first three cost groups. Okay, how did we go forward regarding the traffic and deployment model? The basis for this is a heterogeneous traffic map, which is based on a certain average traffic demand, which has been estimated in the project. And there is some kind of variation introduced here according to a certain correlation model, which can also be observed in real-time environments. So now, based on this traffic map here, we have to implement a certain radio propagation model and also a strategy for the deployment of different radio access points. So this picture here shows just one example for deployment. So the blue squares here indicate a very regular base station deployment according to an hexagonal cell model. And it might be the case that in certain areas here where you have a high traffic demand indicated by the darker color, you can't cover all the traffic demand. That is, for example, one of these areas here. And in these areas, we have to do something else. So in this strategy, we deploy some additional relay nodes here to cover all the traffic. This is then done in the areas of high traffic density. This is only one strategy, of course. You could also try to place the initial layout for base stations following the initial heterogeneous traffic demand, etc. That's only one scenario we investigated. Now, okay, shortly coming back to this, you see here that the initial base station deployment has a certain base station density, regular base station density across the scenario that we are looking at. Now, if we vary this density here, it is clear that if we lower the density of the base stations, we will need more relay nodes to cover the constant but heterogeneous traffic that's kind of obvious. So if we increase the base station density, less and less relay nodes will additionally be needed. So we have a kind of interchange in this scenario between base station density and relay nodes density. And the question is now, what would be under the cost constraint, the optimum densities of base station and relay nodes to cover this area here. So if we now make a plot of all valid densities of base stations on this axis and relay nodes on the vertical axis, then we get a certain curve of valid deployment densities here. So the question is now, at which point on this curve delivers the cost optimal deployment? So just as a side note, the base station density B0 here corresponds to a base station only deployment where you don't need any additional relay nodes. So we call this curve actually iso-performance curve because each point on this curve delivers the same resulting network performance. So now, to arrive at the cost optimum point, now it is of course relevant what the total cost of a base station is compared to the total cost of one relay node. So the ratio of the total costs of these two access point types is important. And we can then draw a so-called line of constant cost, which reflects